Welcome back. Now before we get started talking about radiative forcing, I want to kind of cross two vocabulary words off the list here, and that is the troposphere and the stratosphere. The troposphere and the stratosphere are two vocabulary words, and we're going to need to use those words later in this particular part of the lecture here. There are two layers of the atmosphere. The troposphere is the part of the atmosphere that is closer to the ground, basically from the surface to about 10 or 11 kilometers up. And everything that you and I call weather happens in the troposphere. Clouds, rain, the jet streams, all that kind of good stuff here. And that's going to be important for the kinds of things that we're going to be talking about that are like pollutants in the atmosphere, because down there in the troposphere, it's possible they can get washed out by rain. That's in contrast to up in the stratosphere, which extends from about 11 kilometers up to about 50 kilometers up. Nothing weather happens in the stratosphere. There's no clouds, there's no precipitation, there's nothing like that. If a pollutant gets up into the stratosphere, it's very hard to remove it because there isn't things like rain that's washing the pollutants out of the air. Okay, so we're going to be needing to use words like stratosphere and troposphere, or their adjectival forms, the stratospheric and tropospheric, in this part of the lecture here. Now, where we left off in part one was we were saying that this idea of an imbalance in a system between the energy coming in and the energy going out of the system is going to lead to one of the most important vocabulary terms in climate science, that is radiative forcing. We actually often abbreviate radiative forcing RF. We're going to define radiative forcing as the change in the change in the difference between E in and E out for the planet because of some kind of change that's been imposed, like adding greenhouse gases or changes in the flux from the sun and so on, but we'll get there. So if we actually wanted like a kind of mathematical definition here, we're going to use that symbol delta to mean like change in, like how something changed, and we're going to define radiative forcing as the change in the difference between E in or E out. And you can just use algebra and distribute that delta symbol there, and it's the difference, it's how the energy in changed minus how the energy out changed when you made some change to the system. Now, by definition, it's kind of a little bit of it's a little bit pedantic, but just so you're clear, RF is defined to be before the system comes to its new balance, okay? We have just added greenhouse gases. Now, eventually, the E in and E out will come back into balance, and we'll achieve a new temperature. That's not what we're talking about. We're talking about, we just made the change, like adding greenhouse gases. How is the balance between energy in and energy out changed, okay? So there's our little definition here. Your book gives an example that kind of makes it easy to start thinking about this. For example, they said in the book, speculate, what if the sun just increased its output by 5%? Okay, how would that drive the climate of the Earth? Well, they actually worked through the numbers and the problem as to like how many watts per square meter that is. That would increase the radiation arriving into the surface of the Earth by about, into the Earth system by about 12 watts per square meter. Again, why they came up with that number, that's not the point here. But energy out wouldn't change originally. Now, in the long run, of course energy out would change. In the long run, the planet would get warmer, and because the sun got hotter, and the Earth would get warmer, and it would start emitting more radiation by Stefan Boltzmann's law, but we're not there yet. We're saying, no, I just cranked up the sun. How does that change the energy balance of the Earth? And so in this case, energy in changed by 12 watts per square meter. Energy out didn't directly change as a result of this. So our radiative forcing is just 12 watts per square meter. Okay. It is a way of expressing how much climate change something can cause, like in this case, increasing the sun by 12%. Eventually, of course, the temperature would adjust so that energy in and energy out matched, but that's not what we're talking about. Right now, we're just talking about the imbalance that happens when the change happens. This is actually pretty slick. Radiative forcing is a great term in climate science because it kind of gives you a way to compare apples to apples, okay? It's awfully hard to say how much climate change is methane responsible for, or El Nino, if that's a term you know, or carbon dioxide, or whatever. This gives us a way to compare them. We can compute the radiative flux of carbon dioxide, methane, the changes in the output of the sun, whatever, and get a new number that all has the same units. We can directly compare what is the most important forcing. And along the side here, I've listed 4 kinds of ways that we can have a radiative forcing in the atmosphere. And we're going to take apart each of them and determine, like, okay, what kind of forcing is this? What causes it? How big is it compared to the other ones? And so on. Let's start with the trace gases. Okay, the trace gases are the greenhouse gases that we are adding to the atmosphere, and each of them has its own value of radiative forcing that can be computed. It's all based on solid physics background, okay? That's called Lambert-Beer's law, for what it's worth. And the Beer's law is, uses literally the physics of molecules of carbon dioxide and physics of molecules of methane, and based on their size and the quantum transformations that can happen and so on, we can determine how much it's going to be absorbing and how much it's going to be emitting and all that, transmitting and all that. This is going to be based on like the concentration of these gases in the atmosphere and the physical, chemical properties of these gases and so on. None of this is open to debate. Okay? Scientists aren't faking this. This isn't an opinion. This is experimental results. So I made a whole big list here of key trace gases in the Earth's atmosphere and their associated radiative forcings that we are able to obtain using, these kinds of Lambert-Beer type calculations and so on. And you can see that these are all gases that we have talked about previously to a greater or lesser extent. Carbon dioxide, for example, has a positive radiative forcing. It is increasing the strength of the greenhouse effect. It is making an imbalance between energy in and energy out in such a way that the planet is warming. And so does methane. Now, methane has a concentration like 1,000 times lower than the concentration of carbon dioxide, but methane is a much more effective greenhouse gas. And you can see that in the end, methane is not as big does not have as big as a radiative forcing as carbon dioxide, but still pretty big. Nitrous oxide, which comes from a number of sources, mainly from pollutants associated with transportation, has another very small but positive radiative forcing. Halocarbons, the things that used to be in spray cans and styrofoam and stuff like that, but are still used for certain manufacturing processes and so on. Also have, even though those concentrations are on the order of parts per trillion, because those halocarbons are such good greenhouse gases, actually their radiative forcing is, comparable to methane. Okay, and what does that work out to? About 1/5 as much, about 20% as much as carbon dioxide. We put gigatons of carbon dioxide in the Earth's atmosphere. There's a whole lot of halocarbons still in the atmosphere before we outlawed them for, consumer purposes, and they have a large greenhouse effect. All right, then we hit ozone. Now, here's where we have to use our words tropospheric and stratospheric. Ozone that's down in the troposphere is purely a pollutant, and we have done, we've added ozone to the atmosphere through processes, industrial processes. It's part of photochemical smog, things like that. And it's a greenhouse gas, and it adds about 0.35 watts per square meter to the radiative forcing from trace gases. On the other hand, we've done things that deplete ozone in the stratosphere. That's the good ozone that's blocking ultraviolet radiation and preventing skin cancers and things like that, and we're depleting it. Plus, it's a greenhouse gas. So depleting it, well, it does make a negative contribution to the radiative forcing. Alright, so we've depleted a little bit of the ozone in the stratosphere, and we've added ozone to the troposphere, and you can see together it adds up to a net heating at a rate of 0.3 watts per square meter. There's also this business of water vapor in the stratosphere. There really shouldn't be any water vapor to speak of in the stratosphere. The stratosphere doesn't have weather, it doesn't have clouds, it doesn't have water vapor that evaporates off the surface of the ocean, can't get up into the stratosphere, anything like that. But as you learned back in the methane lecture a couple modules ago, water vapor is a byproduct of the oxidation of methane in the stratosphere. And so just breaking down methane produces, each molecule of methane produces 2 molecules of water vapor, I believe. Anyway, that happens in the stratosphere, so we have this source of water vapor in the stratosphere that's completely anthropogenic. Water vapor is a greenhouse gas, and so it drives a little bit of the total radiative forcing. In fact, it's positive 0.07 watts per square meter. What I want you to notice from this table that I produced here is that while it's true that carbon dioxide is the most important of the anthropogenic greenhouse gases, if you actually add all the other ones together, you get almost the same, not quite, but almost the same radiative forcing. It's 1.35 watts per square meter. This is going to have interesting consequences when it comes to policy. I mean, we can't just think about fossil fuels. We have to also think about methane, and we have to think about halocarbons, and we have to think about ozone and so on to all be part of the solution if we're going to come up with a solution about climate change. Now, before we start addressing some of the other ways in which we have to we can compute some of the other factors that influence the radiative forcing of the climate, let's do a couple more questions real quick. Question 3. Which trace gas in the atmosphere has the largest value of radiative forcing? Carbon dioxide, methane, halocarbons, or nitrous oxide? Alright, make a choice from those 4 and get a little feedback before you move on to question 4.